is a large and difficult field. So we're just going to like barely scratch the surface and look at a couple of interesting things we can do with the tools, some of the tools we've already learned about. So to start off with, what is natural language?
Languages that we speak.
Yeah, so natural language would be something like English or French or Spanish. It is not structured, or it's maybe loosely structured, in contrast to a language like, Python. We have really good tools for like structured language processing. What would we call those tools? A compiler is an example of one. And maybe more generally call them parsers, which take a structured language and turn it into something that's a convenient format for processing. If we have structure, like it's pretty easy to take that language and understand what the meaning is and do something with it. Okay. So translate it into machine code or whatever. Natural language is really hard to understand. We all seem to be able to do it really easily because we've been practicing for 20 plus years, but it's hard to do. Okay? So what are some of the issues that we have to deal with?
There's more than one language.
So there's more than one language. We will restrict ourselves to one language. So today we're just going to talk about English. Even if we're only dealing with one language, we have a lot of issues.
Inflection.
What do you think?
Inflection.
Like the tone of voice. Okay. So that's a hard problem. We'll skip that. We're just dealing with text.
Context?
Context. Yeah. So what do you mean by context?
The words you say have different meanings in different contexts. I use the same thing.
So this sentence here, she doesn't like that one. Does anybody know what that means? Okay. So if we look at this in isolation, there's no greater meaning that we can gain from it. We have to know who she is and which one she's talking about. So we have to like understand the context of this sentence in a larger bit of text. So we have references between things. We have ambiguity, right? Multiple different ways of expressing the same idea. We have if I take out one word here, right, the meaning totally changes. Right, so I kind of need to look at, it's really hard for me to do operations locally without some sort of global context. So maybe, can we use the tools that we've been talking about in this class for any sort of analysis? Say like maybe like KNN or something. So those are kind of hard to work with.
Do like sentiment stuff, right?
So yeah, let's say so one task we might do in NLP is called sentiment analysis, and we want to know like we get a Yelp review and we want to know if the text is positive or negative. Okay, so what kind of problem is that?
Decision tree?
So that's one technique we could use for it. So generally, or with more general term for the problem of determining, I have some input and I want to know if it's a positive or negative sentiment. So it's a classification problem, right? So we have tools for classification, so decision trees, or KNN or SVMs. Right? So let's say I want to throw KNN at this. I have a whole bunch of movie reviews or Yelp reviews or whatever. and I want to predict for a new review, is it a positive or negative review?
Different words, scores, look to see where your cluster is.
Yeah, so in order to do KNN, what do I have to, like, what sort of operations do I have to be able to do with my data points in order to do KNN?
You have to be able to place it in a space, like relative distances.
Yeah, I have to be able to compute distances between them. Okay. How do you compute the distance between two movie reviews? So they're probably different lengths, right? The authors probably have different, writing styles. So it's really hard to come up with a function that takes two movie reviews and tells you that they're, 0.5 distance apart. Right? So the tools that we've kind of talked about for data analysis so far kind of work best with, easily comparable quantitative data. We saw now, we've seen how we can deal with categorical data, but we have to be able to do math type operations, right? And natural language is not convenient to do that with. So there's kind of two paths we could take. One is we could develop a whole system of classification tools and whatever that are built to work with the natural language kind of directly. So you can imagine, so like I take this review and then I do like sentence diagramming with it or something like that, where I kind of approach the problem like I would if I was an English teacher, and I'm like trying to understand the natural language directly. And then from there, I'd have to come up, figure out, okay, how do I use that to do classification? So I, need some special purpose tool, algorithms, whatever, to do these types of tasks. And people have done that. If I spend 1,000 person developer years working on one of these great tools, and I can do sentiment analysis on English movie reviews really well. And then my company decides that it wants to expand to China. Right? I'm going to have to redo a whole bunch of that work, right? Because all of that stuff that I, hand built is going to be really, really tightly tied to the language that I'm analyzing. So it's not really transferable, and it's pretty hard. So there's a theory or a conjecture that has been assumed to be false and assumed to be true at kind of different levels over time, which is that all human language has there's a simplest common mutual language that all human languages share at some level. And it's unclear whether that's true or not. People change their minds about this, but since we don't know what it is yet or know about it, right, we're going to have to do special purpose tools for each language that we want to process. All right, so that's one approach, is we just say, okay, NLP is its own problem, and we'll just develop tools that work directly on the natural language, and come up with our algorithms to do that. Another approach is to say, okay, well, we have all these tools for classification, and whatever other tasks we need to do. So why don't we just figure out how to take our natural language and squish it into a form that we can use an SVM on. Okay. And that seems to be the popular approach these days. is basically how do we turn natural language stuff into basically a point in some weird high-dimensional space. So I take this sentence, or paragraph or document, somehow I turn it into a vector, whatever that means, and then I throw that into an SVM and get something out at the end. So that's kind of one of the popular approaches today. There's a popular algorithm called word2vec that does this. We're going to look at a simpler model today called the bag of words model. But these basically, they take language, turn it into a vector of some sort, and then we can just use our data analysis tools directly on this form. So we'll look at kind of a mix of the two techniques today. So we'll look at some like directly working on language type tools that are maybe going to be useful for analysis. And we will look at how we can transform our language into something vector-like, and see how well we can do with KNN or SVMs or something like that. Cool. So any questions on kind of the high-level ideas of what we can do with NLP? Okay, cool. So let's take a look at some code. So Python is now like, a cool popular language for doing data analysis with the Jupyter notebooks and all that stuff. Long before that, it was the natural language processing language. There's a really great library called NLTK, the Natural Language Toolkit. So we're going to look at a little bit of NLTK stuff today. This has been a very popular library for quite a bit of time. Yeah, some NLP tasks. So we're today just going to look at kind of exploratory analysis, and then we'll look at sentiment analysis, so predicting whether a bit of text is positive or negative. But some things we do, part of speech tagging. So this seems like it would be pretty easy, but it's not, right? Because words can have multiple uses. We want to understand context. Yeah, this is actually harder than it sounds. Information extraction is like, you can almost think of this as compression. So we have we want to take in like a news story, and we want to get like the 3 bullet points that say what happens. So this is about like summarization is one use of this. Sentiment analysis we'll look at. Semantic parsing. This would be kind of like the sort of like what a compiler does, is it takes translates the input language into like a lower level language that's convenient to do like optimization or code generation with. Same idea here, semantic parsing. We have this like formal representation of like what the verbs and objects are and how they relate to each other and that kind of stuff. Yeah, those are some NLP tasks. Machine translation, I guess, is another one. So that's kind of a mix of information extraction, right? You have to understand what the input text is, and then generation of the target language. So that's kind of a different challenge. So that would be like maybe it's sort of like a compiler of language. Okay, so we're going to use NLTK, and it comes with a whole bunch of modules and a whole bunch of stuff. The first time you play with it, it might take a while. So, and then we're also going to use the scikit-learn for doing some machine learning stuff today. So, what we're going to do is we're going to the NLTK book package has a bunch of sample texts in it. So, for example, we have Moby Dick. We can look at all of the words in this in the book. Another one in here. Where are the So the examples we have here are Moby Dick, Sensibility, Bible. This is like all the inaugural addresses for all the presidents up through, I don't know where it stops, but it goes pretty long. The chat, I think, is like just some collected internet chats. The script for Monty Python, some personal ads in the paper. I'm not familiar with this one. This is all either public domain stuff or stuff they were able to collect off the internet. There's a pretty wide range of English text, right? You would imagine that the presidential inaugural addresses are pretty different from internet chat stuff. So here we go. We got Moby Dick. We can use the kind of basic Python stuff. So there's 260,000 words in Moby Dick and 17,000 in Monty Python. We can count word frequencies. So we have in the Monty Python and the Holy Grail, they talk about swallows 10 times. That's a pretty basic thing to know, is just the counts. The next thing we might want to know about it is, okay, what's the context in which it appears? Right? So that's this concordance function. And so this is going to show us basically the context around the word swallow. So here Arthur is talking about migration, talking about carrying coconuts, velocities, different types of swallows. So we know kind of, so this can tell us for the word swallow, right, we're not talking about the verb, we're talking about the noun, the bird. So, the concordance helps get us that information. Moby Dick, Ishmael shows up a lot. Another thing we can do is see which words have similar context. Okay. So in Monty Python, African and unladen appear in similar contexts. Again, talking about swallows. So if we look at the common context, we see the script contains the phrase an unladen swallow and an African swallow. And again, we can look at the concordance as well. So those are kind of just basic exploratory things. Another exploratory tool is the dispersion plot. So this just shows us where in the text words occur. So here we're going to look at some words that we expect to see in presidential inaugurals. and just see, basically because these are ordered by president, this kind of gives us a timeline view of who's using what words. And so on the far left, it's going to be George Washington's inaugural, and then on the far right, it's going to be, I don't know how far it goes. So if we look at this, we see that we kind of forgot about citizens for a little while in this period and remembered again recently. Freedom was not on the early president's mind so much. We forgot about duty. We got more religious as time went on. So we can see some, in this case, because the word location is related to time, we can get some insights that way. So here we're going to look at just this is Washington's inaugural. So this is what he had to say. Yeah. So we can also look at some statistical stuff. So the frequency distribution is going to basically count the number of times the words occur, and we can see the most common words, or how many times a particular word occurs. So this is for Moby Dick. We see that comma shows up a lot, comma and period, very popular. Most of these words aren't very interesting. These are examples of what we call stop words, which are kind of filler. They're not real content. So we'll talk about how to throw those out a little bit later. We see that whale shows up 1,000 times. I think that looks like the only one in here that's kind of not a stop word, the whale. We can look at, to get a unique list of words, we can just use the set function in Python. So this makes a set data structure. And then we can, so here we have a nice list comprehension. So we're just going to get the long words. Is there Melville, not a fan of brevity, I guess. Big fan of circumnavigation. Shows up like 4 times. So yeah, stop words, not all that useful, so we kind of like to get rid of them. The NLTK includes basically a list of stop words for various languages. So we can use these and we can filter based on them. So these are the English stop words. These are words that won't give you a whole lot of use or a whole lot of information. What about these ones? Any ideas? What? Yeah, so these would show up in contractions. It looks like we split on apostrophes most of the time. So this is like the end of a contraction that we don't care about. It looks like it's inconsistent too, because some of the contractions actually show up. Cool. So we can use the stop words to filter out those kind of useless words when we're doing some sort of analysis. So we're going to look at the most common words that are not stop words and are not punctuation. Okay, so we're going to filter out, we're going to keep the words that are not in stop words and that start with a letter. So now we see, we saw whale already in kind of that sea of stop words. And these are some of the other ones. It's a good triplet right there. Okay. So we'll look at, let's see which of these authors are using the most filler words. So what we're going to do here is we're going to look at all the stop words. We're going to throw out the stop words. and just see the fraction of what's left. So if the whole corpus was stop words, we'd say there's like 0% content. So we're just going to look and see what that is. So it looks like Moby Dick is 60% content. This one is the personal ads, right? People are not wasting their space, their limited words in personal ads by putting the and whatever other stop words in there. So, and the number 4, I think 4 is the inaugural ones. So they're only half content. So we just one other kind of useful thing, we've looked at these words kind of as lists. It's really easy to turn it back into a string if we want to do that. So here I'm just joining, I'm just putting all the words in a list together with and separating by spaces. So that's kind of useful. Okay. So another interesting thing we might look at is basically what words show up together a lot. So the collocations basically tell us, what pairs of words show up together. So here we see sperm whale, Moby Dick, white whale, Captain Ahab, ivory leg. There's options, there's parameters I could pass for like how many of these I want. Okay. So that's one other kind of just kind of exploratory analysis I might get. So this would be useful if maybe you're a journalist and you get this big batch of emails and you're just trying to figure out like what is in here. Right? So this might help. Cool. So any questions about any of these kind of basic tools? Okay, so we're going to move on to more challenging or onto a task that we might want to do, some more directed task. So here we have a bunch of movie reviews. So we have basically a movie that they're associated with, the text of the review, and then a label saying if it was a Rotten Tomato or certified fresh or rotten. I don't know where these came from, but so yeah, they're labeled with a good or bad at the end. So thumbs up, thumbs down. And so basically what we want to do is we want to predict from the text whether or not the user liked the movie or not. So that's our goal. So we have a data set. So here's our movie reviews. So it has 2,000 movie reviews. And so they have, so they're labeled with whether they're positive or negative. So these are just text files. Here's some positive reviews. Just look. So we have 2,000 reviews, half positive, half negative. So we'll just look at an example of this. So movie The Mod Squad, which is currently bad. So this is going to be this movie number 3 in the list. And we'll just look at the reviews for this and the categories. So this looks like somebody didn't like that. There's a good one. It's a good one. Character enacting nothing spectacular, sometimes even bordering on wooden. Claire Danes and Omar Epps deliver their lines that they're bored. Avoid this film at all costs. So this is a negative review, as you can imagine. So here's some highlights from the review. So the idea is we want to take, if we see sentences like avoid this film at all costs, we would like to be able to predict that this is a negative review. All right, cool. So what we're going to use here is called a bag of words. And so what we're going to do is we're going to take these reviews, we're going to turn them into a vector, and then we're going to do just our basic classification algorithms on those vectors to do the classification. Okay. And so the way the bag of words works is we're going to look at a bunch of reviews. We're going to pick out like the most frequent words from all the reviews. So I think here we're going to look at like 1,000 or 2,000 words. Okay. And then for each individual review, if it contains that word, we put a 1 in that spot of its vector, and otherwise it's a 0. Okay. So basically we're going to get vectors, binary vectors, and the vectors, the ones say basically which words show up or not. It's a little bit weird. We could use counts. We could say like, count the number of times the words appear. But instead, for a lot of these types of algorithms, we actually just have a binary, does it occur or not? Any thoughts on why? So one thing is, if you have a short review and a long review that have similar content, we would like them to be considered close to each other, right? So by making this a binary thing, we're kind of trying to remove length from the equation. Okay. Another thing is we have this like 1,000-dimensional space, right? If our vectors are length 1,000, right? Maybe having a 1 or a 2 in a particular dimension doesn't matter so much. Okay. So for whatever reason, a lot of these techniques use like a binary representation of a vector instead of like a count-based thing, and seems to work pretty well. Okay. So that's what we're going to do. So first thing we're going to do is we're going to figure out what words are going to be the row of our vector, right? So avoid or terrible or awesome or whatever. And then we're going to convert each of the reviews into a vector with 1s and 0s corresponding to the words they have or don't have. And then we're just going to throw those vectors in one of our classifiers and go from there. Yep.
This doesn't have any context at all, right?
So no context, there's no sense of ordering, nothing like that.
Somebody refers to everything as not awesome, it's going to say that it was positive.
Yep, for this particular classifier. Or it might, if everybody does that, then awesome might be considered a bad.
And we're not avoiding stop word.
I think we're going to skip out of the stop words, but we'll see. I can't remember exactly what we did. So, yeah. So we're going to grab all of the reviews. And then, so right now they're labeled as positive or negative. And it's actually a list of categories, even though there's only one category for each thing. It's positive or negative. Just doing a little bit of data shaping. And we're going to just convert those into 1s and 0s. So we're just going to transform our labels from a list of strings to an integer. So if we run this, we'll see that. So the negative ones, which are the first, all the negative ones come first. So we look at the beginning of the list, these are all negative reviews. These are all positive reviews at the end. So our y vector is just for each review in order is it positive or negative. So the next thing we're going to do is we're going to grab all the words in all the reviews. Okay. So we're going to get the words for each in each file. So we're going to make a big, gigantic list of lists where each row is going to be all the words in one review. This takes a little while because it's 2,000 files worth of words, and it's so this is the part of the extract of that review for the mod squad. Okay, so next we're going to get the most common words. So we're going to use the frequency distribution we saw earlier. So we're just going to lowercase them to kind of get rid of capitalization. And we're going to get the most common 2,000 words in the reviews. We're going to throw out the stop words. So we're going to keep any word. So the word tuple here, it's the word and the frequency. So we're going to keep that if the word itself is not a stop word. And then punctuation marks we're also going to throw out. So we're going to keep the ones if it starts with a letter. Right? So we're going to throw out punctuation as well. Right? And look at the words, the most common words that we see after filtering. We have film, one, movie, like, good, character. Okay. So these seem like they might be useful for us. Right? We might be able to predict a review depending on what words of these show up. Okay, so now we're just going to grab the words, throw away the frequencies of these, and it looks like after we threw out the stop words, we still have like 1,800 words. So that's pretty big set of features. And so what we're going to do is we are going to now take our documents and transform them into a vector by setting a 1 in the appropriate position if the word shows up and a 0 if it doesn't. Okay. So we have a document. We get a set of all the words in the document. We make a 0, an array of zeros of the length of our number of features, and then we set that that value to be 1 if the word is in there and 0 otherwise. So let's just look at. I think this is the mod squad review. So we're going to get the features for these, and then so this is our vector, and then we're going to go back. So we're going to figure out, based on the 1s and 0s in the vector, which words did those correspond to. So that's what this where basically takes gives us the indices of all the 1s, and then we're going to use that to look up which words those correspond to. So these are, this is our big long vector. So there's words. These are all the words that from our common list of words that happen to be in this review. So, however memorable, hair, kind of weird, costumes, Claire. So see if the presence or absence of Claire Danes is a good thing or a bad thing for movies. So well, we've transformed our review into this vector, right? And that vector basically says it contains these words. But we can work with this. This is something we can throw at a classifier. So we're going to do that for all the reviews. We're going to make a big matrix. Okay? So we have we're going to make a matrix with a row for each review and a column for each of the features, so each of the words in our bag, and then we're just going to set each row for each document. And if we run this, so we see that the first 5 reviews, they mostly all contain these common words. So right now these are kind of sorted by occurrence, right? So the uncommon words looks like none of these had, and the common words looks like most of them had. Yep.
So that array is 2,000 by 1,800. So each of those is a list of a list.
Yes. So it's a 2,000 by 1,800. So there's 2,000 reviews, and we have, after we threw out the stop words and the other stuff, we have 1,800 features. Yeah. So if we do KNN on this, do we think bucketing is going to be a good choice? 1,800 dimensions, so probably not. So something like a KD tree is probably a better choice. Okay, so we have a classification problem here. So now we can just throw this X matrix that we made into KNN and say go. And so this looks just like all the other classification problems we said. Say, hey, I want a KNN classifier, my X's and my Y's. And we're going to do 10 cross-validations. So we're going to split it into 90%, 10%, 10 times with different 10% left out, and just see how what our accuracy looks like. So at this point, right, we're not doing NLP stuff anymore, really. We're just doing a normal K nearest neighbors classifier. Our points that we happen that we're looking up came from transforming a document into a vector. Yep. So looks like we're getting like 60% accuracy, which maybe we can decrease the number of neighbors a little bit, see if that changes stuff. And slightly worse, so it looks like 30 is probably a better choice. But better than a coin flip, right? So this is doing something, right? So that should be promising, right? So that's good news. Let's try an SVM. So we'll do the same thing. We use a SVM. I'm only going to do 5 of these because it takes a lot longer to train. Just run the SVM. So that's 1. Do people think this is going to do better or worse? Well, yeah, so SVMs are a lot better. They're like pretty magical, I would say. It's kind of amazing how well SVMs work. So 80% accuracy, that's pretty good, right? From a really stupid model, right? It's just what words are there, right? We're not taking account into the relationship between words at all, right? This is just what words are in the review, and we can hit 80%, which is pretty amazing. Question?
So this was retrained on the same data set and then ran thereafter?
So we're doing cross-validation. So we're gonna
Trained on 5.
trained on 80% and tested on 20, and then left a different 20%.
So is that CV equals to 5 is budget size?
So the C here is the budget. So this is how many times we're doing the cross-validation.
The cable.
Yep. So I trained 5 SVMs on different subsets of the data.
So why is this SVM much larger than KNN like that?
I don't know. I am a little surprised that it does that much better, to be honest.
Does it always SVM is better than
in, or it's just,
I don't want to say always, but it seems that quite often the SVMs do better. Yeah, the SVMs they're pretty amazing. Yeah, we hit 80% accuracy with just a really stupid model, because basically SVMs are magic, right? So we transformed, we did like the dumbest way to transform our text into vectors, and that was good enough for the SVMs. What we're going to do here, we're going to do a train test split. This is, I don't know why we're training a new model. So this is again a model based on 80% of the data. Okay. So we have our SVM here. And then we're going to look at the it's like the first 3 rows, I guess. We're looking at that. So this one corresponds to the mod squad. So this row is the review for the mod squad. We're going to predict based on the features from the mod squad. Okay, so this is, we're just wrapping it in an array because predict expects an array of things to predict on. And we see that we get back a negative review for the mod squad. So for the crappy movie that we looked at, this classifier does classify it as bad. So we were able to write a bad review detector that works reasonably well. Yeah.
No, I don't think so. I was confused. I thought mine was on that was earlier.
Yeah, that was earlier. And so we could plug in the review or the script of Monty Python and treat it as a movie review and see if that is possible. Maybe let's give that a shot. So we want to.
That's like Saturday night. Think of the concept. So in this case, our list of words was built from the movie reviews. Monty Python wasn't included in that.
Yep. So this is like an extrapolation thing. Okay. So Monty Python has 2 of the common words and other stuff. Let's just see. So Monty Python's script is a positive movie review.
That must be a bad model.
I don't know, it's a pretty positive movie. Hard to say. Cool. So so if we want to look at kind of more generally how well this does, since we know that everything is in order, we'll just predict. So here we're just going to predict the first 10 reviews, which are all negative, and we see that only one is misclassified, and if we look at that one, it's actually if we read through here, it's actually it's classified as negative, but the reviews are kind of positive. Ooh, that's not so positive. I feel like there's positive stuff. This is a dark movie. so here, it's like, signs and wonders, feel overloaded with ideas, at least it's willing to stretch beyond what we've come to expect from traditional genre. So this was kind of like a borderline movie, and we misclassified it. So, yeah.
I'm curious to see how our model does on like Edgar Allan Poe short story.
Yeah.
Because that might give us a better idea.
I don't think we have I don't think there's Poe stuff in here. Look that up. Yeah, so our one misclassification out of the first 10 seems like, you know, is a tough one to do. Well, now we'll look at the built-in stuff to NLTK. So NLTK does the transformation. It has, you know, models that are built in. So their technique might be better than our bag of words plus SVM. So we'll just kind of reshape the data for NLTK. And so this is, actually, it looks like we're doing the same bag of words thing. So it looks like it's the same, basically the same data, but just I think it's as a list of dictionaries instead of, or a list of tuples instead of a matrix or whatever. So I think we're still using bag of words here. We're going to use this naive Bayes classifier, which is just another classification technique. And we'll see how NLTK does. And a kind of interesting thing here is that this classifier has a way of telling us basically which features were the most important. So it's going to tell us which words, when present, were the most likely to indicate a positive or a negative review, which is kind of interesting. Look at that. So they got 88%, which is a little better than we did, but not that much. And so if the word outstanding is there, right, it's, you know, 10 to 1, it's going to be a positive review. If it contains Steven Seagal, that's going to be negative. Mulan is positive. Matt Damon is positive. Lame is negative. Wasted is negative. Yeah. Flint, I don't know what that's a reference to, but that's a positive thing, I guess. Ridiculous is a negative thing. So, yeah, this classifier, you know, gives us a little bit more information. So yeah, I think this is also just, it's a different classifier that is, again, using bag of words. So bag of words is a pretty dumb model, but it actually works reasonably well. Kind of the next step up we could go to is what's called an Engram model. And the idea there is instead of looking at words, we look at sequences of words. So, you know, if you could have a bigram model, where we're looking at pairs of words. So, like, you could have not awful, or really bad, or not good, or Matt Damon, or whatever. And then we do the same kind of thing, but we look at the pairs of words instead of just the individual words. Right? That gives us a little bit more context. Right? You can go up, so there's trigram models or n-gram models. There's a Google tool called Ngrams that I think tells you like the frequency of various n-grams over time, stuff like that. Or like search history or whatever. Kind of interesting. Yeah, so we can come up with more complex models that way, or we can use something like a word to vec, which I think takes the whole document and turns it into a vector using some more sophisticated tools. Yeah, so I guess takeaways, if you have to do NLP stuff, it's in general a pretty hard problem, but there's good tools. So the NLTK is a really good place to start. It's got you know, a lot of stuff built in, a lot of good, you know, sample data to play with. Um, I would say a lot of modern stuff uses neural networks to do more complicated sort of custom models, but the sort of non-machine learning tools that we've looked at, just the the SVM classifier or whatever, work pretty well. Yeah.
So I wonder, is SVM suitable for multi-group?
Yes. We looked at an example of that with irises. There's kind of two ways you can do it. And they both require you to train multiple SVMs and then kind of vote at the end. So one way is to train for each class, each output class, train the SVM of that versus other. And then you train a bunch of those and want to vote. The other is to do two class, train a bunch of two class. So if you have A, B, and C, you train an AB, AC, BC, and then you vote, have them vote. So you have to be a little bit, you have to train multiple models. But
I'm assuming it's just a coincidence that we trained on 80% of the data for the SVM, but then we got like 80% accuracy. But how do you know you're not just like matching your training data really well?
Well, we could change the cross validation. So let's say, here, let's just do 3. So we're training on 2/3 of the data. So the accuracy probably goes down a little bit because we're training on less of the data. But we'll see. So still about 80%
So
accuracy.
if you change your parameters and you still are getting the same rates.
Yeah. I didn't look to see, so maybe our choice of C, a smaller C, maybe we'll get higher accuracy. I've decreased my C and it seems to be training a little faster. Talked about makes sense because fewer points are involved, so it didn't look like it had much of an effect. Other questions? Yeah.
So I wonder, since SVM can do multi-group and it works for many cases better than KNN, so why do we still use KNN? Is there any circumstances that we want to use KNN?
My answer is probably. I suspect there are data sets where KNN works better. KNN, I think, can be faster to train. So there might be computational reasons you might want to use one of those. Yeah, and the KNN handles multi-class in a more straightforward way too. Right? We just have multiple candidates on the ballot, and we don't have to like train the model many times.
So I wonder, why is KNN faster to train? I mean, we need to build a tree, but SVM, we really just need to store the kernel function and
Well, so to train it, what we're doing is we're fitting a hyperplane. So we have to find the best. Basically, there's like one parameter per dimension, and we have to find the best. It's an optimization problem. So we basically start by guessing in a slab, and then we like adjust it, like move it and rotate it until it's perfect. And that optimization can take a long time.
One more question about the natural language itself. So I wonder, can we detect those ironic language?
I think that's pretty hard to do. I have no idea how you would go about doing that and how you would detect like whether things are sincere or not. That seems you want like a sincerity analysis, which humans are bad at that. So I don't know how you would train a machine to do that, but like if you had enough data and enough context, maybe you could do it.
So do we have data for this kind of judge negative or positive stuff? If we have a database to say, when you say PHP is the best language in the world, and according to my database, that is real from truth, then you are being ironic.
That could, I guess that, I think a system like that would be hard to build, but so you could probably do it. Yeah. So having the context to know what is true in the world would be helpful, but that's a big amount of context.
So we don't usually stick database with natural language learning.
Probably depends on the application what sort of context is provided. So I know, like the IBM Watson when it was on Jeopardy, like they trained it on all sorts of crazy stuff so that it could like understand the jokes and the like language games in the clues. And I guess it worked pretty well, but it's a big, complicated system with just lots of information sources to get all the context. And as I understand, it has basically been a failure at its original goal, which is like medical advancements.
Misdiagnosing.
Yeah, so it beat Ken Jennings, but not cancer, I guess. You guys know that Ken Jennings is a computer scientist, right? He's got his CS degree from BYU. Yeah. Cool. So probably I'll see more of you tomorrow. Some of you on Friday, I'm guessing.